So we can use the combined method here and take care of this. Well, shouldn't we just use the combined method here and take care of these uncommon ions? We aren't. You know, uncommon ions, we aren't going to factor. We don't have any equation. If we had the equation for these, you know, and the K value for that, then we could take care of it as well. Maybe we could do the combined method, except the combined method would fail in that case, you know, because, and we would have to use the simultaneous approach. So, in other words, this, to make a long story short, we have to be wary of our calculations because due to non-ideal behavior, right, our calculations might be in error. Well, that's nothing new because you had to do the exact same thing with the ideal gas law, right? Does the ideal gas law work for everything? No. No. If you have things that deviate from ideal behavior, the ideal gas law is going to be way off. The same thing here. If you have things that deviate from ideal behavior, then these calculations might be way off, right? Well, what types of things deviate from ideal behavior? Things that have high charge, right? That you're going to expect to see. All right. With that said, that probably doesn't give you much comfort, right, in or confidence in your calculations, just to know that they're going to be somewhat right. And so if we have something like PBI2, you know, how do we handle all this? Well, the calculation is going to be quite horrendous for something like PBI2. And so to handle all these simultaneous equilibria, do you know what we use? We don't sit there and calculate it by hand because that's a lot of equilibria that you got to calculate. And so do you know what we use? We use Visual Mintech because Visual Mintech will do this. Visual Mintech will take care of activities, that is, you know, these clusterings or pairings or whatever. You know, activities, we're looking at clusterings of this. This is uncommon, will also cause deviations from ideal behavior. Then the effective concentration is going to go down. And so in Visual Mintech, we're just going to let the computer do the calculation for us. And so in Visual Mintech, what they do is they update the database as a database with KSP values and activities in there. And that's updated continuously every year. A new one comes out, I think, and maybe even more frequently than that. And Visual Mintech is used by professionals who deal with water chemistry. And so one of the professors here, Tom Stewart, who also teaches Chem 1B, was telling me that they bid on a project for NASA, and it was for the space station. The space station in the cooling system, they're getting precipitates in the cooling radiator or whatever, heat, I forgot what it was, heat exchangers, something like that. And these precipitates were causing damage. You know, something was being corroded and something was being deposited. And so they're trying to figure out what the heck it is. And so he was telling me, well, they were using Visual Mintech to model, you know, the solution chemistry on the space station cooling system, because it's not just water, they have a whole bunch of stuff in there to improve the efficiency for that. And so this is a system that, Visual Mintech is a program that was developed using funding from the EPA, and they made it free. You know, the people who developed it made it free for everyone to use. And so it's one of these crowdsourced type things where everybody, I think, keeps it up to date as far as the KSP and activity values are concerned. But we're going to use it. And so it's not a hard program to use, but it's not an easy program to use. And so there's a little bit of a learning curve, but overall it's an easy, you know, what people consider as a very easy program to use. We don't have any much as far as instructions go for the programs. Okay. You'll see. All right. So this is the non-ideal. And this is the last section that I was planning to cover in chapter 18. We're going to move on to chapter 14, which is kinetics. There's one part of chapter 17 that I didn't get to. Those indicators. And so let me talk about that now so I can get caught up. So this is back in chapter 17, although we already had the test for this. I didn't put indicators on the test though, because I covered it in the morning, but I didn't get to it. Did I talk about indicators? I did? Oh.
So they're intermediate.
All right. Shoot. All right, I need to talk about this in the morning. So I got it mixed up. So we talked about indicators. Now we're going to go on to chapter 14. Kinetics.
What is the salt effect?
The salt effect? The salt effect is the same as the uncommon ion effect, and it's just a Le Chatelier's shift. So for example, if we're looking at this, silver chloride, solid, what is it most soluble in? Is it most soluble in water, acid, or sodium nitrate? What would you guess it's most soluble in? Or sodium chloride? I would guess it's most soluble in sodium nitrate because of the salt effect or the uncommon ion effect. I would guess it's most soluble in sodium nitrate because what's going to happen is the silver ions will be surrounded by, especially if I have a high concentration, I need a fairly high concentration of nitrate. So the silver ions should be surrounded by waters, but let's say a nitrate comes by. It's going to be attracted because this is positive, this is negative. And so we got some kind of ion pairing going on here. And so more nitrate. And so what happens is if silver ions all of a sudden get surrounded by nitrates, then they can't react with chloride to go back to silver chloride. And so what happens is this, the nitrates interfere with silver ions from doing its normal job of precipitating out with chloride. However, this is not an actual bond. This is just an electrical attraction. That's all. And therefore, we aren't going to have another equation. We got to take this into consideration, and that is, what is the activity of silver ions in pure water versus the activity of silver ions in sodium nitrate? It's different, right? The activity of silver ions in pure water would be higher or lower than the activity of silver ions in sodium nitrate. The activity of silver ions in pure water should be higher. That is, silver ions should have a higher effective concentration in pure water than in sodium nitrate, because the effective concentration of silver ions, this is the free silver ions surrounded by water molecules, is lower in sodium nitrate, and therefore its activity is going to be lower. And so what happens is we get a Le Chatelier's shift. If you start removing free silver ions and start clustering them like this, then this shifts it's going to shift to the right. The silver ion concentration goes down, it makes it more soluble. And the same thing happens with chloride, except chloride are going to be surrounded with sodium ions. It's a minor effect. This is not a significant effect. Versus ammonia. Ammonia, this would be a huge effect because ammonia doesn't just, interact with it like this. Ammonia actually will attack the silver and remove it completely because ammonia is a Lewis base, silver is a Lewis acid, right? So why didn't I do this? For example, HNO3, shouldn't it be the same here? HNO3 versus sodium nitrate, the uncommon ion effect. It doesn't matter if this is sodium ions or hydronium ions that are clustering around chloride. Well, the reason I didn't pick acid was because most metal cations are acidic, and so if we add acid, it should shift it left and make it less soluble, right? Although, you know, what is this Ka of silver ions? Well, we don't bother with that, you know. But, you know, these could have been a tie here. Sodium chloride, definitely not. You know, chloride's going to shift this left, make it less soluble. That's the salt effect.
What's the difference between the two, salt effect and uncommon ion?
They're the exact same thing. The salt effect and the uncommon ion effect are the exact same thing. Salt, because you know why I didn't call it salt? Because sodium nitrate is a salt and sodium chloride is a salt. These are two salts, but they have total opposite effect. And so I didn't call it the salt effect. I called it the uncommon ion effect. That's why. Well, anyway, tomorrow what we're going to do is we'll do a calculation like this. Maybe PEI2 is great. This is a calculation we're going to do tomorrow. We're going to do this by hand with the solubility of this, and then we're going to have Visual Mintech to do the calculation for us, list all the species and the concentration. But I'm going to keep the Visual Mintech lab short since we're combining it with the kinetics lab. Yes.
Is there a way for you to reserve user lab for someone like someone it's not last time?
Mm-hmm. Yeah, you could use it whenever it's empty. We're going to be using the computer lab tomorrow and Thursday as well. All right, for chapter 14, let me leave that up because I'm going to show something in there. Like kinetics, I'm going to keep it simple, so I'm going to go out of order from Petrucci. You know, Petrucci starts off with, you know, some reaction like this: AA plus BB plus ... This goes to product. Usually in kinetics, we just say products, so we don't list them all out sometimes. Because usually the reactant concentrations are what causes the reaction to speed up or slow down. And so let's take a look at this is complicated because we have multiple reactants. And each reactant will impact or can impact the rate of reaction. Therefore, let me give you an example. If we have something that is what we call first order in the concentration of A, it'll be like this. First order in the concentration of A means that if the concentration of A gets cut in half, the rate gets cut in half. If the concentration of A doubles, the rate doubles. So whatever you do to the concentration, the rate does the same. That's what we call first order. And so the example we'll use is if I cut the concentration of A in half, then the rate will be cut by half. Let's say it's second order in the concentration B. What that means is if I cut the concentration of B in half, then the rate gets cut by a quarter. And so that's what we call second order. In other words, it's a square. And so whatever I do to the concentration, I have to square that, and that'll be its impact on the rate. So if I double the concentration of B, then I square that, and it's going to quadruple the rate. Let's say if both, if both A and B are cut in half, then what happens to the rate? If A and B are cut in half, then what happens to the rate? Well, if A gets cut in half, then it should go, half as fast, right? So if A gets cut in half, then the reaction should slow down half as fast. But then if B gets cut in half, then the rate should be cut by a quarter. And so A, we see it slow down. B, we see a dramatic slowdown because now all of a sudden the rate is 1/4 of what it was originally. But the problem is this is the same reaction. It's A plus B yields product. And so how can the reaction be cut in half and be cut in a quarter at the same time? Because it's only one reaction. And so when we look at this reaction, if I cut A and B in half, what's going to happen to the rate overall? There's only one reaction rate, and what is the reaction rate? There is only one reaction rate, right? So, is it possible like this? Let's say A and B get consumed at different rates. Let's say it's a 1-to-1 stoichiometric ratio. And so for every 1 mole of A, I need 1 mole of B. Well, is it possible to consume, let's say, if I consume half a mole of A, is it possible to consume 1 full mole of B? No, it's not possible because it's a 1-to-1 mole ratio. And so where's the extra B coming from? And so there's only one rate here, and that one reaction rate means that when I cut A in half and B in half, then the overall rate is 1/8 the original. And so how do I get 1/8? 1/8 it comes from 1/2. This is to the first order. This is A. This is B. I take 1/2 B, but it's second order. And so this comes out to this. It's a composite effect. This is going to be 1/2 times 1/4, which equals 1/8, which is equal to 1/2 to the third. And so we call this third order overall because in the third order, this third order overall because what happens is if I cut both of those concentrations in half, the net effect is it's going to be 1/2 cubed, which is 1/8. Well, if your reaction is third order, then the complication comes here. Because all we see is this. This is what we see. And so if we see its third order overall, then what does that mean? Can you tell what the order is in A and B? You know, because what we did was we figured out what the order is. I just told you what the order is. But if you didn't know what the order in A is and the order in B is, this is impact. This is observed. You know, the observed is going to happen. And so, well, what does that mean? That means that I cut A in half, and I cut B in half. And I know that overall it's 3. And so what is this? And what is this? Well, this might be 3 and this might be 0. Or this could be 0 and this could be 3. Or this could be 2 and 1. Or 1 and 2. We don't know. We have to figure that out, right? Because all we can observe is the overall impact of cutting those. Well, this is getting more complicated. And so I don't want to start off with a more complicated multiple reactant analysis. We're going to start off with simple. So let's start simple. We're going to restrict to single reactant reactions. What I mean by single reactant reactions is just A goes to product. That's it. Therefore, there's no B to screw things up. There's no C to screw things up. The only thing here is A. And so what you see is what you get. And so if we see second order overall, that means it's got to be second order in A because there's nothing else there, right? Yeah, there's no other influence on overall. All right, so let's take a look at describing the kinetics of this. So we describe the kinetics. Well, we're just saying, you know, if I double the concentration or cut the concentration in half, what impact does that have? That can be expressed mathematically as the rate law. The rate law is written like this. The rate of the reaction is equal to K, which is called the rate constant, times A raised to M. M is called the order. And so if M is 0, then we call it a zero order reaction. If M is 0, then A to the 0 is just 1, right? And we have rate is equal to K. And so there are only three possible options that we're going to consider. There could be more, but especially in complicated reactions, but 3 possible M values. Okay, M equals 0, call that 0 order, and rate is equal to K A to the 0, which is just equal to K. And so we got a constant rate. No matter what we do to the concentration, it has no impact on the rate stays the same. M is equal to 1, we call that first order. And so the rate is equal to Ka to the first power. And so whatever you do to the concentration, you'll do the same thing to the rate. So if we cut the concentration in half, that's 1/2 to the first power, which means the rate is going to get cut in half. When M is equal to 2, this is second order. And the rate is going to show square dependence on the concentration. And so whatever we do to the concentration, we just square that, and that's going to be the rate, impact on the rate, I should say. The rate constant we can get via different means. And so what's the easiest way to determine, the rate law or the order? The easiest way to determine this is something called the method of initial rates. Method of initial rates. To get M and K. M and K. First thing we need to talk about is what is the initial rate? There are 2 ways we can determine the initial rate. One, the initial rate is the slope. Actually, it's the negative of the slope, because rates are always positive. Now let me write that in here. This is going to equal the rate, which is dA, the change in delta A, change in concentration, over delta T. Delta A. Except delta A over delta T is going to be negative, and we don't like negative rates. So what we do is we take the absolute value of that. The slope, delta A over delta T, is constant for 0 order, but the slope is always changing for first and second order. For first and second order, slope is continuously changing. For rate is continuously changing. Therefore, we have to use calculus for that. It requires calculus. But you don't have to have calculus, because we'll just use the equations that come from calculus. Figure it out. So the initial rate is the absolute value of the slope of the tangent at time equals 0. And so what we're just trying to figure out is how fast is this reacting initial. So we're going to have some initial concentration, which we'll call A sub I. That's here. And we want to figure out how fast is it reacting here versus down here. Down here we have some fraction of the initial, and the rate's going to be a lot slower. And so when we look at the curve, the curve might look like this. It could be very rapid and slow down. So what we'll do is we'll just draw like a tangent line at time 0 and say, okay, this is how steep it is right at the beginning of the reaction. If we take the slope of this, it's going to come out negative. So if we take the absolute value, it's going to give us the rate.
Concentration
Yeah, just delta concentration over delta T. That's the slope of this, because this is versus time. So we also call this the instantaneous rate at time 0. Or 0. Well, drawing tangent lines isn't so easy most of the time. So what we might do is we might take the average rate over a time interval. But we got to make sure so we'll take the absolute value of the slope of the average rate when, actually this is not right because this is the slope of the average I'll just put in a quote, when less than 5% reaction has occurred. The rate is a slope, so this is why my wording's a little bit screwed up here. But take a look at the blue line and the black line. Are those two slopes the same? No, because when you have a significant amount of reaction, this is the average rate between this time and this time. That would be the slope here. But if I can tighten it up, and that is, if I have less than 5% reaction, then less than 5% reaction is just right here at the beginning. So if I had less than 5% reaction and I connect those two dots or two data points with a line, a solid line, now take a look at the purple line and the blue line. Are they a lot closer than the blue line and the black line? Yes. And so the closer this is spaced, that is, let's say I had 99% reaction. If I had, only 1% reaction, then it's going to get closer and closer, right? And so the less reaction I have, the closer the purple will be to the blue. Well, what we're going to say is 5% is acceptable. So 5% is going to be a little off, but it's close enough, okay? And anything less than 5% is even better because it's going to be more tightly spaced and closer there. And so what I can do is I can just take a look at the first two data points and see is less than 5% a reaction occurred. And so let's take a look at some data here. See if we can figure it out. These numbers are a little tricky here, but if I look at this, is less than 5% reaction occurred. That might be a little tricky to see. Tricky means you have to use a calculator. Let's see one where we don't have to use any calculator to figure it out. If I look at this, we start off at 1 molar here. After 25 seconds, we're at 0.78 molar. Is that less than 5% reaction? No, that's like 22% reaction, right? And so at 22% reaction, if I took the slope, that is delta y, which is delta A, over delta t, which is delta x, is that close enough to the initial rate? No, because at 22% reaction, we're way out here. And so this purple line is not going to deviate even further. But what about this other experiment here? No, that's 25% reaction. We started at 1, now we're at 0.75. And so we don't have any data here. We got to be a lot quicker in the data collection in order to see it. And so all these, unfortunately, we can't take the average because too much reactions occurred. And since I can't scroll here, let me see if there's another data table. No. And so let's go back to that one we were looking at earlier. Here. This might be easier to see. Let's look at the second experiment. In the second experiment, has less than 5% reaction occurred here. Let's take a look. What's 5% of 1? 5% is 0.05. So 5% of 3 would be 0.15. So 0.15, have I lost more than 0.15? So going from 3, it could go down to 2.85. So we're good. Less than 5% reactions occur here. So if I take the slope of these first 2 data points, then it's going to be like this. We're catching it right at the beginning. So here's the first one, and then less than 5% reaction later, it's here. And so right at the beginning of the reaction, if I just calculate the average slope, that is the slope joining these 2, then that should be pretty close to the slope at the tangent, 0 times 0. Does that make sense?
Yes.
Yes? No? Does it make sense?
So from starting from 0 and then the next data point, take the average of it, if it's less than 5%.
Yeah, or this. This is, let's say this is less than 5%. This is more than 5%, a lot more than 5%. And so if I have a lot more than 5%, let's say I had about 40% reaction, and I just take the slope of this. Which one is going to be closer to the initial slope? That is the slope right at the beginning of the reaction. The first one, because what's happening here is this is changing. So it starts off steep and slows down. And so this first one is going to be closest to the initial. The initial is going to be a little greater, you know, because the slope is continuously changing as the reaction is occurring. And so the closer I can get these 2 data points right to the beginning, the more accurate of an initial slope that should be. Versus here, if I wait too long, and I say, okay, I'm just going to take the average slope here, that average slope is nowhere near my initial. And so this is why we say, okay, within 5%, that's an acceptable way. That way, I don't have to calculate. You know, the other way is I could graph this and then draw the tangent line. But if I graph this and draw the tangent line, is that an easy thing to do? No, it's difficult to do. It's much easier just to go delta y, delta x, and just measure the slope based on the 2 data points here. Does that make sense? Yeah. Okay. All right. And so if I wanted to figure out the initial rate here, this is what I do. I'd figure out the slope here, and then what I do is I double the concentration and see what happens to the rate, right? So if I double the concentration, you have 3 choices. If I double the concentration of A, then the three choices are the rate stays the same, the rate doubles, or the rate quadruples. And so what I'll do is I'll make up a table. The table is going to look like this. It'll be the concentration of A initial, and then we'll have the initial rate. This is not, the rate's always changing, so this is just the initial rate. Right at the beginning, this is the concentration. And so this is A initial 1. It gives us rate 1. And then I'll do experiment 2 where I'll double this concentration. So I have 2 times that. Then see what happens to the rate. So this is what we're doing here. Do you see that? What we did here was we started off the concentration 1.5, and then we doubled the concentration to a concentration of 3. So we doubled the concentration. What happened to the initial rate? Well, let's calculate the initial rate here. The initial rate here is, by the time we get here, the more than 5% reactions occurred, right? So let's see what the initial rate here is. So it's going to be positive, so just it's 1.49 minus 1.512 divided by 1. What do you get for your initial rate? This one here. Yeah, delta A over delta T. Well, rates are always positive, so get rid of the negative. So it's going to be 0.022. Okay. Now we double the concentration. What happened to the initial rate? Which would be delta A over delta T. A quadruple? All right, so the initial,
The rate was
0.089, this was 0.022.
0.022.
So it's 4 times. So if we double the concentration, the rate quadrupled, which means it's got to be second order. Does that make sense? Well, that was a bit of a pain. We had to do 2 experiments and then figure out the initial rate, right? Typically what's going to happen is somebody will do the slope calculation for you. Oops. Okay. And so we could use the method of initial rates for more complicated reactions. But let's focus on just A right now. Because if we have more complicated reactions, then the rate of the reaction is going to be influenced by both A and B. But we can negate the influence of one of those by leaving that concentration the same. So let's take a look at here. In experiment 1, the initial concentration of A is 0.185, B is 0.133, but in experiment 2, they leave the concentration of A the same. So whatever impact A has, it's going to have the same impact in both of these. And so basically we factor out A and we just look at B. When we look at B here, we double B, and then what happened to the rate? So somebody figured out the slope for you because they're giving us the rate here. So the rate did what? So we double B, the rate did the rate double? What's 2 times 335? 6.7. 6.7. No, that's not 6.7. This is this would be, because the exponents are different, this would be going from 3 to 13. So to go from 3 to 13 means that the rate actually quadrupled. You see, 3.35 times 4 gives you 13.5, roughly. And so the rate quadrupled, which means that it must be what order? So we double B, that would be second order. And so it's second order in B. But what is the order in A? Well, to figure out the order in A, we have to leave B the same. So look at 1 and 3. In experiments 1 and 3, B is the same, 133, 133, so that's going to cancel out the impact on B. And then we double A. And so if we double A, what happened to the rate? The rate doubled. That means it's first order in A. So in other words, we did this particular problem. If we double A, that's going to have a first order impact because the rate's going to double. But if we double B, that's going to have a second order impact. Does that make sense? And so in other words, this is first order, this is second order, because it'd be 2 squared as far as the impact goes, whatever that concentration is. What happens if we double both A and B? If we double both A and B, well, A is a first order impact, so that should double the rate. B is a second order impact, so that should quadruple the rate. And so if we double both A and B, what's going to be the overall impact on the rate? It's going to be 8-fold increase in the rate, right? Because it's a third order overall. And so let's see here, if we look at this experiment between 1 and 4, we double A, so A gets doubled. That's going to double the rate. We double B between 1 and 4, that's going to quadruple the rate. And so overall, the rate should increase by 8-fold. And so we're going to come back to this, so I'll talk much more about this later. But A is going to have first order. And so we double A, this first order. B is going to have a second order. And so overall, we expect a third order impact. And the rate should increase 8-fold. So is that what's observed here? So we double A, we double B, and the rate overall goes from 3 to 27. So going from 3 to 27, that's about 3.35. That's an 8-fold increase. That's 3.35, sorry. 3 1/3. Do you see that? All right, so what we're going to do is, like I said, we're going to keep it simple. We aren't going to do the more complicated ones first. We're going to do the simpler ones, and the simpler ones are just going to have one reactant impacting the rate, and that's it. So I guess I'll have to wait until next time to talk about the ways we're going to do this.